The final problem of fall 2017 is question 11, and this is a sorting identification problem. And so these I think are a little tedious, but they're also kind of fun. It's like a little mystery we're going to solve. And so the question states that below you will find some intermediate steps in performing various sorting algorithms on the same input list. The steps do not necessarily represent consecutive steps in the algorithm. That is, many steps are missing. We're not seeing the entire picture. However, they are in the correct sequence or relative ordering. So for each of them, write the name of the algorithm it illustrates on the blank line. Select the algorithm from the following choices. And so our options are insertion, selection, merge sort, quick sort, heap sort, LSD, and MSD sort. In all of these cases, we start with the same input list and should have the same final output sorted list, or in other words, they all correctly sort the list, right? Like this, right? And so we can just sort of go part by part and figure out what they are. So for this first question, we see that we start, and I'm going to first look to see if I notice any like glaring trends of how the numbers are moving. And so we see that, let's see, in this first one, 560 jumps pretty far. And we also see that there's some movement for 112, and some of these like smaller numbers, I guess, are moving towards the front. And some of these larger numbers are moving up. But also some of the numbers have not really moved a bunch. And so we see there's some sort of movement. And so now looking at the options, I would go ahead and probably eliminate insertion sort, right? Because insertion sort and selection sort as well, both of those are options where the list slowly becomes more sorted from left to right? And the sorted portion grows from all the leftmost elements to all the rightmost elements. However, I don't really see that trend happening here. And so I'm going to roll that out, right? Because we just have this like movement sort of all over the place, right? 3, 5, 6, 9 sort of jumps over here. And so I'm going to guess that it's not insertion sort, probably not selection sort. I don't think it's merge sort either, right? Because in merge sort, what we'd see is first pairs get sorted relative to each other. However, that's not happening. We had this big movement right away, so it's not merge sort. Now let's look at quick sort. And so this would take the first element of the sequence as the pivot. And so if it were quick sort, we'd see all the elements less than 2, 5, 7, 6 on one side. Oh, and all the elements that are greater than 2, 5, 7, 6 on the other side. And that's actually definitely what's happening here, at least on this first line. And this sort of makes sense with the general movement patterns I saw earlier, right? Which was that these two numbers sort of jumped all the way to the beginning. And then we had more of the bigger numbers, I guess, huddled up on this side. Okay. So far, it seems like quicksort is a really good option here. And if it were to be quicksort, well, then what would happen? We'd see that eventually there'd be a recursive call on the left side, and there'd also be a recursive call on the right side, where, 5207 would be taken as the pivot, right? And so if we were to have a consecutive call next, we'd see all the elements less than 5207 on one side, which is true, and all the elements that are greater than 5207 on the other side, with 5207 being moved to its correct place in the middle. And so just based off this, I feel pretty confident saying that this one is quicksort. And you could see that if you were to do look at the next steps on your own, that it would continue to work as quicksort. Cool. So I'm going to say this one's quicksort. The other thing is that I have reason to believe that with the 5 parts and the given 1, 2, 3, 4, 5, 6, 7 input options, there's probably not going to be repeats. So I'm going to just not bother looking at heap sort, LSD, and radix sort and assume that those might come up later if they do. Okay, cool. Quicksort makes sense there. Now we're going to look at this next option. And so what's going on here? Well, let's see. We see immediately that there's a lot of movement between the first and second steps. And the list pretty quickly looks almost sorted to me, right? Like we have the 500s, then 1000, 2,000, 3,000s, these are out of order, okay. 4,000, oh, 5,000s, oh, these are out of order amongst themselves, but okay, and then 6, and then 7, 9. And so we see that they're really close to sorted, at least by the most significant digit, right? We see that within the 3,000s and within the 5,000s, we're not sorted, but we get there eventually, right? And so I'm going to go ahead and take a guess and say that this is MSD radix sort. Cool. Now we can move on to part C. So what do we see happening here? Right away, I noticed something odd happening, which is that between the first and second steps, we actually have the biggest element at the front, right? Which is weird and not very close to sorted. And so what sorting algorithms do I know might do that, right? Moving the biggest element actually all the way to the front where it doesn't belong. Well, it could be LSD radix sort, because LSD, we see a lot of weird jumping around, right? However, if we look at the least significant digit, they're not actually sorted on that. So it's not LSD. Our other option here then is heap sort, because heap sort, we said, builds a max heap and then slowly, one element at a time, pops the max element off to the end. And so we actually start sorting the list in reverse order, going from biggest element at the back. And then eventually we sort from right to left. And so just based off the fact that this huge element jumps to the front first, and then eventually quickly gets popped to the back, and we see sort of what looks to be the heap shuffling over here, and then another pop, I'm going to say that this is heap sort. And again, I know I'm going a little fast, but you can always try running heap sort, and you will see that these steps do all appear along the way. Again, emphasizing that as you do it, you're going to notice these. This is popping off max element. These are restoring the max heap property, right? Because we need the biggest element at the front. And so we saw that when you pop the biggest element, right, the last element moves up to the root, and then you have to swim it down and restore the max heap property. And so now we have a proper max heap, but again, where the biggest elements at the front. So these are fixing up the heap, and then we have another pop max here. And then at this step, we're again restoring the heap property because 560 moved up to fill the spot. However, 6833 is the next biggest element that should actually be at the top of the heap. Cool. So we're going to move on to part D. And what is going on in this one? Well, let's see. We actually see, I don't think anything changes between the first and second steps. But if we look at the next steps, what do we see? Well, 3291. So at first, these elements, okay, were sorted, and then 3291 moves all the way up here. Okay. Does anything else move? Let's see. Nope. Okay. 3291 moved back. Cool. Then we look at the next step. So between these two, what happens? Let's see. Okay, and we see 5012 moves back, right? I don't know why I drew it like that. And it swaps places with 5207, and nothing else changes. Okay, what happens in the next steps? Let's see. Oh, 5901 moves back, right? And we see that also 9744 ends up here, and 6833 moves back there. Okay, and then we keep going and we keep going, and we see that eventually 560 sort of scoots all the way back, and so on and so forth. And so because we saw this pattern of elements sort of starting from left to right and slowly moving backwards, I'm going to go ahead and guess that this is insertion sort, right? If we think about our two algorithms where we saw that pattern of like moving from left to right, they were insertion sort and selection sort. But we know that selection sort would put 560 at the beginning right away. and build it that way. Insertion sort, however, is going to just swap things backwards as they need to. And so we saw that this process happened. We skipped a few steps in between some of them, but overall, this is insertion sort. Cool. And now the final sort of the evening, we see that there is some interesting, I guess, like movement patterns, right? If we look between the first and second steps, the only thing that changes is that, let's see, where'd this go? Wait, I lost something. Oh, these two elements move places, right? Everything else is kind of the same. Okay, what about between the second and third steps? Okay, now we see that there was actually some movement over here, right? And what about between the third and fourth steps? Now we see there's been a ton of movement over here, and so on and so forth. And so what I'm noticing specifically here is that we had small movements, and then they got a little bigger. And now as we're looking at this whole portion of the list is actually just sorted, right? And then what's the next movement? Oh, a little pair of movement over here. And then a group of movement over here. And then more and more and more. And so what I'm realizing is that this is a pattern that sort of falls in line with merge sort, right? Because we see pairs swapping and then sort of groups of 4 swapping or whatever, like more and more and more. And so this falls in line with merge sort. And now that I have this theory, let's go see if it actually falls through or works out. And so we see that first we break it down into the smallest case of all these 2 element lists, right? And we see that at the next step, what do we have here? We sort these, and actually I think if we were sort of taking a recursive approach where we looked at the left first, all of these are sorted. And then if we look at merging these, we would see that if we merged these 2, oh wait, let me think. I'm trying to figure out the merging pattern actually used here, but I feel like this all falls in line with being merge sort, because again, we sort of start with these smaller sorted subsections. Then let's see. This whole thing becomes sorted. Okay, yeah. These are 2 sorted subarrays. I think the way it's doing the merging exactly is maybe a little bit of an odd order. Yeah, I'm having trouble figuring out exactly the order that it's processing like the recursive merge sort calls in. However, in general, it's definitely following the patterns of doing small subarrays sorted and then suddenly, oh, look at half the array is now sorted relative to each other. And then we're going to start on the other half of the array, slowly sorting these, right? And so now we have this and these that are relatively sorted, right? And that's the pattern that merge sort follows. And eventually it's going to merge the whole thing. And 560 will eventually move up there. But we see merge sort starts with very localized movement. And then as the subarrays get bigger and bigger, we see bigger movement. And so this one is merge sort. Cool. That is all of this problem and the end of the exam. So good job, have fun, and drink some water.